Hey everyone, Mr. Woods back again, and we're looking at our example problem from this worksheet packet. Looks like there's an awful lot of work here. There's really not. There's just an awful lot of really big diagrams. Um, and the equations are pretty basic and pretty simple. I don't think you'll have too much of a problem with this. So again, we're dealing with the idea of ideal mechanical advantage. That's mechanical advantage dealing with no friction, and that's basically just a ratio of the distances, the input distance and the output distance, or the effort and resistance distances. In a perfect world, that would be the mechanical advantage. However, since we're going to overcome friction, we have to apply a little extra force on the input to overcome friction. So then we're dealing with actual measured forces would be the actual mechanical advantage. So the resistance force over the effort force. Notice that those are flipped in relationship to each other. And then finally, efficiency, comparing the mechanical advantages, the actual versus ideal mechanical advantage, or work output versus work input to give us a percent for efficiency. And then it goes on to give us examples for each of the types of simple machines. So for an inclined plane, right, we have the resistance distance, we have the effort distance, we have the resistance distance, so it's just a matter of dividing it out. Let's go ahead and look at 4A here. We have an effort distance. We're putting in 24 meters worth of work. It's only moving 5 meters, so 24 over 5 would very simply be our mechanical advantage. And that's 4.8. And remember, there is no unit with these, so it's not a naked number, it's just a proportion. Down on the bottom here, they give an example for you for actual mechanical advantage, right? Dealing with the resistance and the effort forces in this case, but obviously we'd need a spring scale to measure these. Since I'm guessing you don't carry a spring scale around with you, they give you one in the diagram. So if we're pulling with 15 newtons up the ramp, and it'd be a 35 newton straight weight, resistance divided by effort, so 35 divided by 15, or 2.3 mechanical advantage. To get to efficiency then, let's go ahead and jump all the way down to number 6. You need both of those things. You need both the distances and the forces involved because we want to compare the ideal and actual mechanical advantages. I think it's a little bit easier working with this equation with the work output versus work input. So that's what I'm going to work with. Yeah. So we figure out here the distance and the effort. So this would be the input work, right? And then we have the output work, right? So work output, it moves a 783 Newton object, a distance of 2 meters. So that's our work output. The work input is moving a 150 Newton with a Newton force, 12 meters. So calculate this out. 783 times 2 divided by 150 times 12. And I get 0.87, but remember it's a percent, so boom, boom, 87% efficient. That's pretty darn good. All right, taking a look at some of the other things, right? We have mechanical advantages in levers. That's all just distances. Distance from the fulcrum to the load is your resistance force, or resistance distance. Distance to where you're actually pushing on it would be the effort distance. So effort divided by resistance. Very basic, very simple. Same thing with mechanical advantage here. Actual mechanical advantage, right? You're putting in a force of 47 newtons. You're actually lifting with a force of 327 newtons. That'd be the weight of the object. So again, dividing that out gives us an actual mechanical advantage based on force. And then again, I'll go ahead and do number 9 with you, finding the efficiency of the object. Again, actual divided by ideal mechanical advantage. You could figure out works in this case, but this time it's a little bit easier doing mechanical advantages. So the actual mechanical advantage is comparing the forces involved. The resistance force divided by the effort force. So the actual mechanical advantage would be the resistance force of 45 newtons divided by the effort force of 57.7 newtons. So that is the actual mechanical advantage. That's the top part of that. The ideal mechanical advantage is dealing with the distance ratios, where we have the effort distance over the resistance distance. So the effort distance would be the 5.8 meters. The resistance distance would then be the 6.3 meters. And I hate mixed fractions in an equation, so I'm going to simplify that before I do anything else. 45 divided by 57.7. So that's 0.78. And then 5.8 divided by 6.3. 0.92. Calculate that out. 0.78 divided by 0.92. 0.8478, blah, blah, blah. Significant digits times 100. 85% efficient. Again, pretty easy to do. Hopefully this makes some sense for you. Again, with pulleys, we're dealing with the number of lifting strands. In this case, there's a 2. In this case, there's only 1. In this one, you're dealing with the Newton force, that kind of stuff, and then the pulling force. We're dealing with a mechanical advantage again. Yeah. Pulleys, and more pulleys. Pulleys are simple because all you're doing is counting forces. Oh, let's look at efficiency. This is pretty good. So efficiency of a pulley system is going to be that actual mechanical advantage over ideal mechanical advantage again. Pause for a second, I'm losing stuff. Okay, so again, efficiency is the actual mechanical advantage over the ideal mechanical advantage. Ideal mechanical advantage is really simple with pulleys. 1, 2, 3, 4, 5. 5 lifting strands, so that is your ideal mechanical advantage. Actual mechanical advantage being the relationship of the forces. The output force in this case, or the resistance force, is going to be 100 newtons. The input force in this case is going to be 22 newtons. So 100 newtons over 22 newtons, and then divide that by 5. And of course, times 100 to make it a percent. We have a 91% efficient pulley system. Pulleys are usually very efficient. All right, that was problem 12 if you're following along. More pulleys, more efficiency of pulleys. Wheel and axles is pretty easy. I don't think I'm going to bother going through that with you because, again, it's just like levers. The distance of the wheel and the distance of the axle. Radius or diameter, doesn't really matter. And I think that is it for the worksheet. All right, so if you have questions on that, get a hold of me, let me know. Otherwise, have a great day.